Chapter 2, first order differential equations. Again, the first thing we're going to start with is finding these solution curves without knowing the solution. So this is what's called qualitative analysis. There are three types of analysis that you do to a differential equation. One is qualitative. The other two, there's one called quantitative. Quantitative, three T's. Which, by the way, happens to be my favorite, because that's numerical analysis. That's approximating a solution without being able to find the solution. There are plenty of differential equations that don't have a closed form solution, but we can still approximate what it looks like. So qualitative and quantitative involve looking at the answer without knowing the solution. And then the third, the best of all worlds, is what's called the analytical analysis. Is that right? That doesn't sound like the right. Quantitative analysis, the qualitative analysis, and then the analytical solution, I guess, would be the best way to write that. Because analytical analysis sounds very redundant. Right? What other kind of analysis would there be than an analytical analysis? But an analytical solution means finding the actual closed form equation, formula, for the function that satisfies that. Hopefully explicit formula, but sometimes even implicit, finding the equation. But once you understand, if you just go back and think about what a differential equation is telling you, you can answer some questions about how a solution behaves near a point. And I'll get to that when we start talking about direction fields. How does the solution behave near some point on the graph? And then the other questions that we'll be able to answer without finding a solution is what happens at the endpoints. What's the long-term behavior of the solution as either x or maybe even time, whatever the independent variable is, goes to infinity. And we don't typically talk about going to negative infinity with time. We're talking about an evolving system from a point forward. But you can also do it for static equations as well that don't depend on time. Okay, so here's what I mean with the question number one. How does it behave near a point? Look at this differential equation that I've got written right here, this guy. The left-hand side of that equation, dy dx, is the derivative. Now, graphically, geometrically, what does the derivative of a function mean? Slope. Slope of? Of a tangent line to the curve at a point, right? It's the instantaneous rate of change, but graphically it's the slope at that point, right? As you zoom in to a point on a curve that's continuous, it looks more and more like a line. That line's slope is the derivative. So let's say, for example, I don't know what the solution to this differential equation is, but if I've got a graph and I want to say what would a solution near this point right here have to look like? Well, just think about it. Let's have a dy dx over here that's, say, x minus y. Let's say that point is 1, 1. What would the slope of a solution that passed through 1, 1 have to be? Flat or zero. Now, you don't know if the curve stays flat on both sides, but we do know that near that point, the slope would be horizontal, right? Near 1, 1, the slope of any solution has to be 0, or close to 0. Actually, at the point, it has to be 0. But on either side of it, it may move quickly. We don't know what happens away from 0, but we know near it, and exactly at it, it's 0. Okay? Now, the thing is, we don't actually know if a solution passes through that point. So what we're going to do is we're going to build this grid of all these little lines that will say, if the solution happens to be there, I know what the slope is at that point. That's what's called a direction field. For a given solution, y of yx, and a specific value of x, then f evaluated at those 2 points, like in this case, f of 1, 1. That's f of xy, And so this number right here is f of 1 comma 1. That's what I'm talking about right here. That will represent the slope of the tangent line to the solution at the point x comma y, or x comma y of x. And I just want to draw one more time to emphasize this. If you've got a curve, y of x, okay, then here's your x, here's the output of that x. This height would be y of x, okay?
What is that written next to the y in the solution of the point xy?
X, y of x. Just emphasizing again that y is a dependent variable. Okay, so at this point right here, right, there's a slope. So, and the slope of this line is f at x comma y of x. Now what we're going to do again is we're basically going to decide on some grid of points on a given coordinate system, and we're going to plot those little lines at every single one of those points. These lines I'm going to refer to as the lineal element at that point. So we can construct a grid of lineal elements that will represent what the slope of the curve at individual points looks like on the plane. Now we can do this the easy way or the hard way. The hard way means by hand. In fact, I'm not even going to draw it on the notes. I'm going to come up to the board and just draw for you what I'm talking about. The hard way would be. Say I want to do the direction field for the differential equation I have on the screen over there off to the right for a grid of points ranging from -2 to +2 in the x direction and -2 to +2 in the y direction. And let's do it at a resolution of every half unit. Okay? So every half unit means I want to put a lineal element at every one of those points, and then also every one of these points here. And I'm just drawing, you know, how many points is that going to be? 1, 2, 3, 4, 5, 6, 7, 8, 9, 81 points I've got to draw on all over this thing. And then what I'm going to do is at each one of these points, I'm going to plug in its coordinates into f. And then draw a little line that represents the slope at that point. So at 0, 0, for example, it's horizontal. 1, 1, 1, 1.
Count through. Have that drawn out for us on what it's not.
Do what?
We did these in count through. We just didn't have to draw them ourselves. They were drawn out nicely and well designed. It was like, show us what the function looks
Yes,
like.
and that's where your homework's going to be in here, although I've got a couple of tools. In fact, that's what I'm going to point to you to do next. In fact, that's what we're going to do next, is play with the ones that will show you how to draw them yourself. Okay? There's 2 tools that I'm going to walk you through. In fact, 3 of them. Because nobody in their right mind would do this by hand. Now, I had to draw these by hand when I took differential equations whenever I was here, because technology had not yet progressed to the point that it has now, that there are so many varied and sundry tools out there for you to use. All right, so to build this grid, instead of doing it by hand, I've got 3 tools. One is a demonstration software package that actually I would encourage you to install on your own machine at home for when you're doing your homework, because occasionally throughout the semester there are going to be some demonstrations that you're going to use and reference in your homework. Now you can come into the lab. I spent a couple hours yesterday making sure every computer in this lab has this thing called the Wolfram CDF player. It's basically a little piece of software that will run some simple demonstrations from the textbook. So when you go to this link, and I'm going to take us there in just a second, there'll be a place for you to view the CDF file. It's not like a PDF file, only it's a computational document format instead of a portable document format. And it's got interactions and sliders and things like that that you can use. And there's a lot of them that go along with the textbook. And I'll even show you in just a minute where you can find access to all of these example tools. The best one for your homework to use is actually this third one I've got in your browser. Come on, Bowser. Brower is not a very good typo. If I put Bowser as a typographic, that'd be more awesome, but it's not. Also, Maple has a tool in it to build these direction fields. But again, you have to have access to Maple, which means you'd have to come into the lab and use it here or over in the computer lab in the library. I did try to set up, and it failed miserably because not everybody was able to do this, a way for you to remotely access Maple. So I've made this course not dependent on Maple, with the exception of maybe a few small cases or in your projects. But this tool right here is going to be the best one to use, because you can actually, on the demonstration up here, he has a finite list of differential equations to select from and then look at their DEs, their direction fields, DFs, whatever. Maple, you can type it in, but you have to come to the lab. This last one you could do in your browser from anywhere, and allows you to type in the differential equation into it, and then click on it to see different solution curves. Okay, so let me exit out of my OneNote here, and I'm going to go into my browser. In fact, I'm going to release the computer to you, so that you could go play with these as well. Let's start with the Wolfram demonstrations. So the link is there. You'll have to type this out, but it's demonstrations.wolfram.com/slopefields. Oh, I typed it wrong. Maybe it's case sensitive. I just want to see if it actually goes. There it is. Yeah, if you don't type it in case sensitive, then it takes you to
Search results.
a search, and it's just the first one in the search. If you did this in Internet Explorer, I haven't tried this in Firefox on here. This actually allows you to run a little add-on in the browser. I noticed on my computer in my office, if I was running Chrome, I actually had to click this download the demonstration as a CDF and open it. It opens automatically in that Wolfram CDF player once you have that installed. To get the free installation, I've given you a link to it of the CDF player to install it locally. I'm just going to click allow here at the bottom on my Internet Explorer. And hopefully that will allow this thing to run right here in the browser. Okay, so now you've got a series of choices, like x minus y is one of them, y minus x is another. And so here's the direction field automatically being drawn for you. And this particular tool allows you, again, to choose from a series of differential equations, this finite list of fairly simple differential equations. And as you select a different one, so say I went down and selected x plus y. It redraws it and shows me the direction field. I have the ability to modify and select different ranges, so I can let my x go from, say, -5 to +5 by just dragging those around. That was right here. I can also change my range for the y's, say from -5 +5. It's kind of annoying. If you want to get an exact number in there, you'll notice there's a little plus sign next to the slider, and you can go in and type in a specific value if you want to. just rescaled its size for me. I'm just going to leave it there. I'm not going to be too picky about it. Okay, so I'm going to move these to 5 and -5. Go ahead and change it back to x minus y, up at the function that you're working with. Just so happens to be what I have in your notes. I'm not actually going to write anything, I don't think, in your notes. I just want you to be able to play with this tool and be able to recreate. You can change the number of lineal elements horizontally and vertically. So say I wanted 20 by 20. That just creates a finer grid. Okay, now one of the things that I think is kind of cool about this is that you can actually approximate with some just drawing what the solution is going to look like. Let's say I'm going to draw a point. I'm just doing this by hand. Let's say I know that I start right there. That's my initial condition. What should happen for a curve is it should pass through this field without ever intersecting any of my lineal elements. If it gets close to one of those little elements, it needs to be at the same slope. So notice how you're trying to navigate almost through a maze of these things so that you stay close, but don't ever intersect them. So it looks to me like a solution that goes through that point would have to look like that. If I had started, for example, down here, my solution might look more like this. Both of those are solutions to the differential equation, but they're two different particular solutions. Okay? And I could do that all over the place, right? Get one that goes down like this. I think these all kind of fold through there. Those all look like solutions to the differential equation to me. Okay? So let me release that and come back here. You can actually show an exact solution. That point that I first picked was about 2 or 0, 2, right? So I'm going to display an exact solution, and I'm going to move where that initial condition is. So it's 0, 2, or close to it, 2.1, which is exactly what my guess looked like, right? We're pretty close to what my guess looked like. Wonder if I can, well, I can't overlay what I did before. So that's the demonstration tool, and again, it works with all these different differential equations in here. In Maple, I'm not going to open Maple, but there's a task built into Maple that lets you do basically the same kinds of things. I'm going to encourage you to play with that on your own, although you don't absolutely have to. Let's open up another tab, and let's go to that second link, or I guess the third link that I gave you, the third tool. Bit.ly, bit.ly is just a shortened URL. I actually had to go and spend a couple hours yesterday finding a new tool because the ones that I had used, the previous courses I've taught, were all Java-based, and most modern browsers now are anti-Java. Chrome won't even load at all anything Java, so I wanted to give you a link that would be HTML5 or at least JavaScript based so you could use it. That's what this one is. And it turns out to be, in my opinion, just as good or better than the one I'd used before. So let's go in and let's type in the second differential equation I have on your page there, which is sine of y. And then just hit enter, and it redraws a model differential field or a direction field for you, a slope field. Both mean the same thing, direction field, slope field. You can adjust on this one. We start by default with just one ODE. Later in the semester, we'll talk about slope fields for systems, actually direction fields that represent your two-variable system in the same kind of way. Let's say we move our x's to go from -10 to +10. And let's do 30 segments horizontally. And let's go -10 to +10 with 30 segments vertically. What I like about this, different than the Wolfram, obviously, is I can type in the equation up here, but I can also click anywhere on the graph, and it will draw the approximated solution through the direction field based on the point that I chose. You can also see as you hover your mouse over to the left-hand side, underneath where it says enter XY, right here, it says, or click on the graph. As you hover over it, gives you the points. So if in your homework, for example, it says, let's find what the direction field looks like for this particular differential equation, you could come here, type it in, and then it says, what does the solution look like that passes through, say, the point 0, pi. Well, I'd go to 0, 3.14 roughly, which is actually not that far from where I just drew one. And then you can draw a whole bunch of them. What I like seeing here is you're getting now a feel for the fact that when you have a differential equation that has an infinite number of solutions, that doesn't mean that every curve is a solution. But now you have a whole family of curves that satisfy that differential equation. Every single curve that I've drawn on this screen, and every curve I could possibly get by clicking on this screen, actually satisfies this differential equation. Each of them is a solution to one and only one initial value problem, but they're all solutions to the differential equation. You can also save that image or open that up. Say you wanted to copy and paste this into a document as you're working on your projects. Maybe one of the parts of your project would be to do a direction field for your model so you could look at what some of the solutions look like, analyze some of its stability, which we'll talk about what that means later. You can click on that, or you can just right click on it and it takes a picture of that image. Well, it's supposed to. It says right click on the thumbnail and save that picture. So you could do that to actually get the picture and you save it locally. Okay? I like that tool. That's my favorite of the tools. I can hear that. Everybody's clicking like crazy. There's a few already built models down here. There's something called the undamped pendulum, which the pendulum model is the model of the angle theta is the is the vertical axis, and the horizontal axis is time. So this x would be time, y would be theta. So if you move a pendulum and let it swing, so if you start at 0, 0, nothing will change, or I was just a little bit off 0, 0, and now it forms these different.
Is it a glitch from those funky things?
Yes, there are glitches. Now the reason there's a glitch is that it's not using the solution to actually find the graph. It's not solving the differential equation for you. It's basically doing what's called an Euler method, which I don't talk about until the end of this chapter. But an Euler method works like a different direction field in that you know what the slope is at this point. So what you do is you start at a point and go straight in that direction some length. So say I decided to start here and I went this far. I've got a new point here. I've got a new slope. I'm going to follow that point. And so it's approximating by taking these little tiny steps along the way. Now, that's not the actual solution, because the only way that would be a solution is if your size of your steps went to 0. So it's got a small number plugged in, a tolerance of probably 0.01 or 0.001. And so when you get to a certain place, you can find a place where the method fails and it does something stupid, crazy. Okay? Numerical analysis is the whole field of studying where the points are that make it do something stupid, crazy, so you can stay away from those. Okay, I've got 1040, so I'm going to stop there. And what we will do next time is pick up and talk about just some terminology for the rest of this section. You can actually go ahead and get started. I think you probably have some of the information you need to be able to start the homework for 2.1. But I'm going to end there, and we'll pick up where we left off on Tuesday. So you guys have a fantastic weekend, and we will see you after the break.